Hello and welcome to another brief demonstration of OCL-related technologies working with UML models in the Mars release of the Eclipse Papyrus project. Today we'll look at model-to-model transformations using the QVT operational mapping language. So let's start with an overview of a very simplistic UML meta model for relational database models. In this model, I have a schema class. The schemas can contain any number of tables. Tables contain columns that are described by a type and some kind of width. Types describe the basic data types offered by a particular relational database system. These are all named elements. They are things that can have names. In addition to columns, tables have keys of various kinds: primary keys, unique keys, foreign keys. A key covers a number of columns, and a foreign key in particular references the primary key of some other table, mapping its key columns one for one with the columns of the referenced primary key. For that reason, the column end of this association is an ordered set. It's unique and ordered. And additionally, a table might want to be populated with an initial bunch of rows via insert elements that have an ordered collection of literal values to be inserted into the columns of the table. So we'll see how that is used for populating lookup tables in our simple transformation. So the idea is that we have a meta model for relational database schema models, and we'll want to transform simple UML class models to this simple relational database schema model. Now, of course, no good meta model is complete without a library model to accompany it. And in this case, we have just a very simple model defining a suite of common data types supported by most SQL flavors of relational database. So things like, the variable with character strings, numeric types, dates, and so on. So a very simplistic example of a relational database schema model. So the idea is to take a UML class model, such as our by now very familiar, extremely simple banking system model, and transform that to a database schema. So classes will map to tables. The primitive valued attributes of classes will map to columns in the corresponding table. Associations will map to foreign keys. The primary key of a table will be determined by the attributes that are flagged as being an identifier attribute. So UML properties have an isId attribute that indicates that they comprise in some way an identifier for the objects described by that classifier. Persons have identifying attributes in the last name and the first name. Enumerations are interesting. We will map those to lookup tables in which each row of the table corresponds to one of the enumeration literals, and an attribute of that enumeration type, like the account kind, will map to a foreign key to that lookup table with just an arbitrary numeric ID column as its primary key. So let's have a look at what such a transformation might look like. So we declare two model types, UML and our relational database schema model, as the input and output types respectively. Also, an input to this transformation is a particular instance of an RDB model serving as the SQL types library, in which we'll look up types for reference in the output model. So the main entry point of this transformation is an iteration over the extent of the input UML model, grabbing out the root packages and mapping them to schemas. So in a similar vein to the model to text templates that we saw in our previous demonstration of transformations with Xelio, in QVTo we define mappings as a kind of an operation in this extension of the OCL language and semantics. So it is like an operation in that it is defined in the namespace of a class from one of the input or output meta models, and it produces some result that generally is a new or existing object in the output model. So in this case, we have a mapping of packages to database schema. So this mapping creates a new schema as its result implicitly, and we populate the properties of that result object by assignment, which is a semantics that does not exist in OCL, OCL being a side effect free language specifying constraints and values. This is more of an imperative type of language, like a programming language, but a bit more abstract in some key ways. So the schema that we generate from a package gets the same name as the input package. We iterate the types in the UML package that can map to tables using this isTable query operation, and we map them to tables and assign those to the tables of the output schema. Then there's a second pass, once we've generated all of our tables, to iterate over the classes in the UML package to generate foreign key relationships for the associations between those classes. The to-table mapping is defined in general for any type, and specific mapping inheriting that for classes. So it inherits the mapping that sets the table name as the UML type name, and further generates columns by mapping the attributes of primitive type in the input UML table, and creating a primary key for, so setting the keys as a sequence of one object, being the primary key, whose columns are the columns that were generated by the two-column mapping for any attributes that are ID attributes in the UML class. So this resolve one in operation is an operation that's applicable to any model element in the output models, similar to the operations of the OCL any type in the OCL standard library that are applicable to all model elements. This is applicable to any element, and it resolves the previously generated output element from the output side of the named mapping that was generated from the target of the operation call being an element from the input side of that mapping. So this uses the traceability information that the QVT operational runtime system maintains as it runs models through these mappings. So what we do here is we find the columns that were previously mapped from the ID attributes of this table and collects them in the foreign key, in the primary key. And that mapping is this one, generating a column from a property in the UML model, bring the name over, and set the column's type and width to standard SQL types from our SQL library model, corresponding to the primitive types of the property in the UML class. Now, another specialization of the generic type to table mapping is for enumeration types. So this was generating the lookup tables that I referred to earlier, in which we always generate two columns, an ID, which is just an auto-incrementing integer value. That will be the primary key. And a name, which will be populated with the literal names from the UML enumeration type. And that constitutes an unique key, so it is indexed for efficient lookups and to assert uniqueness of the values. So we iterate the owned literals of the UML enumeration to generate the insert statements, effectively, to populate the initial values of the initial rows of this lookup table. So the QVT operational mapping language lets us define locally in the namespace of our transformation classes for purposes such as storage of temporary information in-out parameters of a mapping. So we generate lookup rows for the enumeration literals with this primary key set from a counting sequence from 1 to n, creating new inserts whose column values are these ordered pairs of the index and the enumeration literal name to populate the ID and name columns respectively. Foreign keys in the second pass of the transformation resolve tables that were previously generated from a class to create foreign keys for any attributes that are of class type. Those generally are association ends. So for each such table, we effectively accumulate keys as the union of the keys we've seen before, plus a new foreign key. And likewise, accumulate foreign key columns from the columns that are referenced as the columns of the foreign key. A foreign key property, being one of those that is of class type, generates a foreign key by, again, resolving the table that was previously generated from the class that is the type of that column, of that attribute, and finding its primary key as the primary key that is referenced by the foreign key, and grabbing out the columns of that primary key as being the prototypes for generation of columns in the referencing table to be its foreign key columns. And to try to make sure that those names of those foreign key columns will not clash with any other names of attributes already defined in this class, and thus generating columns in this table, we concatenate the referenced table, or the referenced class name, and its primary key or column name. So we'll see how that ends up in the final result. And of course, the type and width of a primary key column, of course, matches the corresponding primary key column of the referenced table. So as we saw with OCL itself, and with the Axelio/MOF M2T model-to-text transformation language, our transformations can define query operations as additional operations of any class in the input or output models for the purpose of reusing expressions and making more concise mapping expressions for maintainability and readability. A type can map to a table if it's a class type or an enumeration type. We have a query operation defined in the relational database metamodel to look up by name a type from the SQL types library model that's passed in as a parameter of the transformation, one of the input models. And we have simple rules for mapping primitive and data types from UML to corresponding SQL data types that we expect to be able to find in that library model. So that's a certain constraint on the models that can be passed in as valid inputs. With our meta model, we do supply an SQL types library model that satisfies those conditions, has these types in it. So not trying to get too fancy, it's a very simplistic example of a small-scale model-to-model transformation using QVTo. So let's try to run it on inputs being this UML model and our standard library model. And it's done. It takes just a blink of an eye. So what do we get as a result? We get an instance of our RDB meta model. The mySchema correctly gets the name of the mySchema package. We get a table for each of the class and enumeration types. They've got columns in them, so we see our account kind enumeration generated a lookup table with an integer ID column and a name column. The primary key is just the ID column, the unique key is just the name column. And we get these inserts for the various enumeration literals that we defined in our UML model. So that looks good. The person has columns for its attributes, has a primary key that, it doesn't have enough columns in it. It has the last name column. It should also have the first name column. Because looking here, the first name also is an isId attribute. So that's a problem that we're going to have to fix. It must be a problem in our transformation. And there's a foreign key comprising the account number that references the primary key of the account table. So that looks good. And that is an integer because the account number here is an integer type. That's good. So if we recall, our account number has an account, a kind, and a balance. Here's the account, the balance. Its primary key is the account number, but we're missing the kind, which should be a foreign key to this lookup table. So that's another problem in our transformation. So let's try to solve what these two problems are. Well, the first one should be a problem with this, where we determine the primary key columns from isId attributes. I see what the problem is. So we're asking to resolve exactly one column that was the result of the property to column mappings, but that's not good enough because there might be more than one. We actually need to resolve each of the different columns that were generated from ID attributes of the input class. So let's save that and try running this again. Look at the result, and now we see, yes, last name and first name both are primary key attributes. So that's good. We fixed that problem. And we have remaining the problem of the missing foreign key reference from the account to the account kind lookup table. So let's see if we can figure out what was going on there. So here's where we generate foreign keys from a class. And I see here that we're mapping attributes whose type is some kind of class to foreign keys, but not also the enumerations. That's not good. So we did have a query operation determining what kind of a type generates a table. So why don't we just reuse that? Because class is enumerations, and maybe we'd come up with others as we elaborate this transformation. So in fact, we should be using that query operation. Is table. Okay, so now that we're generating foreign keys for all attributes of table type, we need to also make sure that when we generate a foreign key from a property, it isn't sufficient now to trace only tables that were mapped from classes. We need to trace also tables that were mapped from enumerations. And that's easy to do because, in fact, both of those two table mappings inherit the same generic type to table mapping. So our traceability graph will include occurrences of that mapping. So that's what we need to use here. We need to find the table that was generated from the properties type, whatever kind of a type that it was. So that should do it. Let's run the transformation again, look at the result. And indeed, here we are. We have the account number still, we have the balance still, we have now also the account kind ID integer column referencing by this foreign key, the primary key of the account kind lookup table. So there you have it. Model to model transformations from UML models using the QVT operational mapping language. Thank you.